Hello everyone, my name is Daniel Sevilla. I'm head of software engineering at Scientific Volume Imaging, and today I would like to talk to you about the new features and improvements that we have brought into the latest Huygens 2104 release. So let me first show you an overview of what will be discussed during the webinar. First, I will extensively talk about the new support for array detector images in the PSF Distiller. Also, with regard to the PSF Distiller, there's currently growing interest in quality assessment, and we have built new tools to do that. Secondly, I will tell you about new tools for easily assembling object analysis workflows. This will also be helpful for reproducing and reusing your image analysis. After that, I will briefly tell you about the new changes in Deconvolution Express. And lastly, I would also like to inform you about the new stitching options. So let's get started with the PSF Distiller. First off, what is the PSF Distiller and how does it work? So the PSF Distiller is the tool to create a real measured PSF from your microscope. A measured PSF deviates from a theoretical PSF and is not perfectly symmetric. It contains the imperfections from the microscope. The way to obtain a measured PSF is to start by acquiring an image of sub-resolution beads. The PSF Distiller will analyze the beads and will extract information from them in order to construct the real measured PSF from the microscope. This process is illustrated in the image on the left. The beads image is loaded into the tool, which detects and classifies the beads automatically into usable and not usable beads. This classification can be seen by a color code indicated here as well as in the tool. Beads marked in green can be further used. Beads marked in other colors show that they cannot be used. They will be discarded due to different reasons that are explained in the tool. Once the PSF Distiller has detected the usable beads, it will extract them, average them, and use them to create the final PSF from the microscope. This can also be seen on the right, where we show the typical differences between theoretical and measured PSFs. The curves at the bottom show the intensity profiles across the center of both theoretical and measured PSFs. This is repeated 3 times along the X, Y, and Z directions. The dotted line for the theoretical PSF shows slightly better resolution than the solid line for the measured PSF. This can be easily understood from the 2 PSFs above. Now, one may still wonder why to take the trouble to distill a measured PSF. So there are basically 2 reasons for doing this. First, to achieve even more precise deconvolution results. So think that because since the PSF is the basic building block of the image, it is important that we provide the deconvolution algorithms with a model of the microscope as exact as possible. The second reason is as quality control. So does the microscope perform correctly? Does it perform as well as, say, a month ago? And how does the measured PSF deviate from the theoretical PSF? Okay, so far I've told you about the PSF Distiller in general. Now I would like to tell you more about what we have added to the tool in the latest release. And starting in Huygens 2104, it is possible to distill measured PSFs from array detector microscopes, such as Airyscan I, Airyscan II, and SPAD. In this first example, you can see the PSF Distiller working on a 3-channel image of multicolor beads acquired with Airyscan I. This system uses a layout of 32 detectors, which take 32 independent images. The acquisitions of all 3 channels and 32 detectors are contained in this single multi-dimensional image. As you can probably see here, the image contains some chromatic aberration, which the PSF Distiller will estimate and report, as I will show later on. Alright, so now the tool will analyze each channel and detector, will automatically find and accumulate beads in order to create a single bead model for that channel and detector. The accumulated bead model will contain more signal, which is advantageous for computing the PSF later on. So starting from the left, we see the 3-channel image of beads. Then the PSF Distiller will split it into the 3 channels and analyze them all sequentially. For each channel, it will find and classify the beads as usable or not usable, as can be seen in the center column. On the right, we see the accumulated model found for each channel. And from this accumulated model, the tool will create the distilled PSF for each channel. So first, the distiller will report the chromatic aberration found in the multi-channel beads. You see that here. Secondly, it will show the resulting multi-channel PSF on the right. Again, notice that this is a multi-dimensional image containing independent PSFs for each channel and each detector. Lastly, the PSF Distiller will give us the option to assess the quality of the PSF. This will also be useful to get an idea of the resolution of the system and how it compares to the theoretical PSF. So if we click on this button, FWHM estimate, we come into the next stage of the tool here. You see that the tool now shows intensity profiles across the center of the PSF and along the X, Y, and Z directions. The full width at half maximum FWHM for each curve is automatically computed and reported. This is a measure of the resolution of the system in each dimension. Optionally, they can also be displayed next to the theoretical values for comparison. These reports can be created for each channel and detector from the detector array. The reports can be exported for tracking the performance of the system over time. As an example here, we see the intensity profiles and FWHM along the X direction for the first channel. Detector 0 is on the left, detector 17 is on the right. In theory, the resolutions of detector 0 and 17 are nearly the same for this system, as you can see here. However, the resolution of the measured PSF is somewhat better for detector 0 than for detector 17. So let's now look at another example, this time with Airyscan II. So here the PSF Distiller is again working on a 3-channel image of multicolor beads, but this time acquired with the Airyscan II system. This system also uses a layout of 32 detectors which take 32 independent images. The acquisition system, however, groups the images from the 32 detectors into 4 concentric rings. Therefore, this single image contains 3 channels and 4 detectors/rings. Whenever possible, though, contact the manufacturer, size in this case, in order to get access to the original 32 detectors containing the raw data. Huygens will be able to achieve much better results with all 32 detectors, also during the convolution. As before, the PSF Distiller splits the 3-channel image and processes each independent channel independently and automatically. The beads are also found, classified, and accumulated automatically. Again, the tool reports the chromatic aberration found in the original beads, the resulting image containing a PSF per channel and detector ring, and we can analyze the PSF by clicking on this button. If we do that, we can compare the resolutions of the first detector ring on the left and the second detector ring on the right. The intensity profiles and FWHM values along the X direction show that both detector rings perform similarly. The theoretical PSFs show slightly better resolution than the measured ones. That's fine. Okay, so far we talked about the PSF distiller, but now let's briefly move to a different tool, but somewhat related tool. What if, let's say, we want to do the same kind of PSF analysis that we have just talked about, but this time on already existing PSFs? So for that purpose, there's a standalone analysis tool that we call the Huygens PSF FWHM estimator. This tool contains the same analysis features that are embedded in the PSF distiller, like comparisons with theoretical PSFs, reports on FWHMs, etc. So this tool may be useful to you for assessing quality changes between old and new PSFs. Another new feature in Huygens 2104 is the workflow designer in the object analyzer. If you're familiar with the object analyzer, you may know that it offers many possibilities for different types of analysis. With a new workflow designer, it's now even easier to create, visualize, save, and load analysis workflows. Thus, reproducing and reusing analysis workflows will be easier too. Here is a screenshot of the new workflow designer for object analysis. A workflow consists of independent tasks, such as setting regions of interest, setting anchors, segmenting objects, filtering objects, selecting analysis parameters, etc. The tasks can be easily dragged and dropped between these two rows, indicating which tasks are available and which tasks are already selected in the current workflow. For each task that we select, there's a panel with options to configure the task, like here. Additionally, the workflow designer makes reusing analysis workflows easier. Loading, saving, creating workflows, using preset workflows, all of this can be found at the top left. At the bottom left, there's a panel with straightforward guidance on how to finish assembling the workflow. Lastly, one can directly execute the currently selected workflow by pressing here. Once the workflow has been put together, we can execute it on any other image. Very well, let me now move on to another tool, Deconvolution Express. In this version of Huygens, we have improved the interactivity of the tool. It should now be faster to select a region of interest for deconvolution. Moreover, we have introduced the concept of acuity, which can also be loosely understood as sharpness. So in this tool, it is possible to select a level of acuity or sharpness for each channel. Fine-tuning these values in combination with selecting a region of interest can be a straightforward way to visually assess and optimize the deconvolution process. Lastly, I would like to tell you more about the recent changes in the image stitcher. We have added new options for aligning tiles, which can be useful for very large datasets or when there's very little overlap between the tiles. This slide shows the stitcher working on a collection of tiles. Here, the tile positions have not been optimized by the tool yet. Therefore, these tiles positions are simply the ones specified in the image metadata. At this point, the stitcher can enter the optimization stage for finding better tile positions. As of Huygens 2104, we offer the following three options for optimizing the tile positions. First, optimal alignment in XYZ. This is the best option and the default one. Stitcher surveys the tile volume and finds the optimal displacement in 3 dimensions. Then only in XY based on the central plane. The stitcher only surveys the central plane, as here, and finds the best XY displacement. This can be useful when the other planes contain little information or when there's little change across the planes. Now optimization, number 3, will tell the stitcher not to survey the tiles for finding proper displacements. It will just proceed to stitch the data, to stitch the tiles simply as indicated by the file metadata. This can be useful for running tests quickly, but should not be used for publishing data. Additionally, we have added options for filtering out hot and cold pixels during the optimization stage. This will not change the final intensities of the stitched image, but will help with finding the optimal tile positions when the acquisition system is affected by hot and cold pixels. Also, the manual vignetting correction, which is based on acquisitions of flat fields and dark frames, has been extended in order to make it possible to use one single plane rather than a 3D stack for these images. We have also added support for the facility line from Aperture. And with this, I would like to I would like to encourage you first to pose your questions via the chat and also to register to the next virtual SVI Huygens workshop next month. So let me try to address 1 or 2 questions depending on how much time we have. And I already see here that somebody asks, how should I record the beads for the PSF Distiller? And this is indeed interesting question that we often receive. It is actually a broad question, but let me try to summarize what you need to do. So first, you need to use sub-resolution beads for the type of microscope that you are interested in. So this can range from 50 nanometers for state images to 170, 200, 250 nanometers for wide field images. You can basically use any of the microscope types supported by Huygens, but do remember to use the right sub-resolution beads for that type of microscope. For wide field microscopy, it's usually okay to image one single bead. For other microscope types, it's usually necessary to accumulate multiple beads. In order to do that, they need to be well spaced, not too close to each other. So this all can be found on a page that we have on our website, which is called, so on our website svi.nl, you can go to recording beads. That's a special page where we explain all these details, and it's absolutely worth checking out. So please do so. It will be helpful. So okay, I think this is what we had time for today. I would like to thank you all for your attention, and I wish you a very nice day, and see you next time. Bye bye.